Client Director here at Godel. Today, I'm joined by Jorge Garcia de Bustos, who is a technical pre-sales consultant across Godel Technologies. Jorge, can you do a little bit of an intro about yourself?
Yeah, of course. I'm Jorge. I'm originally Spanish, but I lived in the UK for about 20 years. I'm originally an electronics engineer, so my kind of background, lots of kind of math, lots of physics, lots of kind of signals, and a little bit of kind of software doing my degree. And very early on, kind of I went into software and became a kind of a developer, and kind of rose to be a dev manager. And for before I joined Godel 3 years ago, I was basically running development teams in different locations, and my role now is to act as a liaison between the teams that we have in our delivery locations and our partners in the UK. And kind of what attracted me initially to machine learning is mostly the fact that the kind of the heavy maths involved and the kind of the way using mathematics and using some of the stuff that I learned when I was in my kind of teens and early 20s, that we can actually build machines that and programs that can to an extent emulate some of our kind of human capabilities.
Fabulous. So you've kind of given the game away there, but the topic that we're talking about today is why machine learning projects that companies undertake often fail. So machine learning, it isn't magic, but what is it all about?
If you think about the way that we typically write software, right? So the way we typically operate in a software development house is someone has ideas about what the software should do. They will have either stakeholders or product managers or people like that who will know what the software needs to do, what are the business processes it needs to support, and we work kind of top down. We think about what the software needs to do. We encode that into kind of a natural language, English in most cases, or Russian in some cases, in the case of our delivery centers or whatever. But the idea is that we first write down what the system needs to do, and we try to understand the business process, the universe, and identify kind of the rules and equations and formulas that govern that behavior. And we write those requirements as in very low level detail, because when we write code, we need that low level detail, right? And then we encode those kind of low level natural language instructions using a computer programming language, okay? And that works well for loads of things. So there are loads of processes that we can encode really, really well using that. But not everything works like that. So I can think, for instance, of situations where it's very difficult for our human brains to comprehend the full complexity of or interdependencies between the things that we are trying to model, or situations where the requirements may involve like thousands or millions even of low-level rules. And I'll give you an example. Imagine that you wanted to write a program that scans a bit of text and tells you whether the sentiment in that bit of text is positive or negative. It can be a review of a product or a film or a piece of music or whatever. I want to know whether the person who made that review is basically displaying a positive or a negative feeling about that. If we do that from requirements, the natural thing would say is, okay, if so-and-so word are contained, it's a positive review, and if so-and-so word is a negative review. But those rules, if you think about the richness of English language and the fact that we can even use sometimes the words in paradoxical meaning, like we can say, this is not very good. If you look for good, you might think that actually the review is good, but the not very at the beginning kind of modifies the overall meaning. So the number of rules that we will have to build if we went for the top-down approach is just insane. So there are problems that are not well suited for our top-level kind of requirements-driven approach. So the idea is that instead of a top-level requirements-driven, we go from a kind of a bottom-up approach, where we basically work with the data. So we choose a core algorithm that is kind of relatively simple but has a very flexible behavior, right? And then what we do is we feed data to this algorithm that very often already has the right answers. So we give the algorithm, these are thousands of positive reviews, and these are thousands of negative reviews. And we expect the machine, based on those, to actually almost like figure out what are the hallmarks, what are the signs of a positive or a negative review, right? And the machine forms a sort of understanding of the universe. It's not understanding like a human being like you and me. It's not, in many cases, it's not even reading the language. It's just literally looking at a sequence of things in a very dry way. But the kind of the accuracy of some of those models can be astonishing, like much better than anything that we would do as basically from a top down approach.
Fab. So obviously that's a couple of the ways in which machine learning can handle this. Can you give me any other examples at all?
Yes, there are like good problems and bad problems for machine learning. Okay, and if you want, choosing the right problem is one of the or choosing a bad one is one of the typical mistakes that people make when trying to apply machine learning. So machine learning is not, we are not trying to build something that has the cognitive abilities of a human. No, we're just trying to build a computer program that will use statistics and maths to kind of build associations between things. And there are programs that are really good fits and programs that are really awful fits. So the good ones are kind of something we call, for instance, something called classification, which is the prediction of whether a data record belongs in a given category, right? And for that, we need to give the program kind of correctly pre-classified historical data, right? And that is really good for things like problems like, I don't know, spam detection, likelihood of loan default or customer churn. So we can tell the machine, it's almost like yeah, we give you this is what happened in the past, and we divide the users between or the scenarios between kind of the positive and the negative, and we say to the machine, okay, you find out what are the bits in the data that are highly correlated with positive and with negative outcomes, so that in the future we can ask you, okay, classify for me data that you have never seen. We can also use that for programs that we call regression, which is the prediction of the likely value for a real world variable given a kind of a historical data series. So we can basically say, for instance, you want to write a program that gives you the market value of a house or a car based on a series of data points. So based on kind of historical data about a particular car model or anything like that, we could actually try to predict a sensible value that you could get for your car kind of in the open market, right? That kind of prediction of a real world variable. And we can also use it for things like natural language processing. So machines have become really good at spotting kind of sequences and patterns in the way that we either kind of when we feed them text or when we feed them kind of a spoken language or like speech. This can be used for things like language translation and sentiment analysis. Machine learning kind of engines have also become really good at image processing. So, and they can do things like identify and locate objects inside and persons even inside images and even generate or reconstruct images that are kind of damaged. So there are certain good problems but it's important to state that kind of choosing a bad problem kind of already sets your machine learning effort on the wrong footing because they, as I said, they don't have magical capabilities.
Fabulous. So with that, let's talk about data.
Mm-hmm. So machine learning is kind of consider it almost like data-driven engineering. Okay, so and for that, it's essential. Like the main thing that we need when we do machine learning is high quality data about the phenomenon that we are trying to model, right? And when I say about like a high quality data, there are loads of things that you need to look for. So the first thing is most machine learning kind of engines, and they need very clean, very consistent, very kind of a very flat data. So it's almost like the equivalent to a nice big spreadsheet with lots of rows and loads of columns and no blanks anywhere. So and also gathered with consistent criteria over time. So if you're feeding one of your models like a time series of, I don't know, 10 years worth of data, it's very important that the kind of the gathering criteria 10 years ago is the same as you have right now, because it's essential to have consistency over time. And many models react very badly to kind of changing of conditions or data that has kind of empty gaps in it and stuff like that. So that's it's essential to have data that is kind of provide or manipulated to a very high standard. And just to give you an example, imagine that you want to predict you are like a company with customers, and you want to build a model to predict their behavior. So the type of data set that you would need to build a model that predicts your customer behavior is something like a single customer view. So this kind of aggregate consistent representation of all the data that your organization knows about your customer. So it's not just a kind of a dirty Excel spreadsheet that you extract and massage manually when you need it. It actually needs to be a real-time or near to real-time data set that is created by a pipeline that is reproducible, auditable, and testable. And it actually needs to be something that you can run not just on demand, but actually done on kind of consistently and with consistent data definitions and no gaps. So you need to have it's almost like a flat presentation where on every row you have each one of your customers, and on every column there is every bit of information that each one of your IT systems actually has kind of scattered all over, right? And only when you have a data set like that with I don't know, thousands of rows represented each one of your thousands of customers, and hundreds or even thousands of columns denoting every bit of information that you know about them, it's only at that point that you can start building kind of sensible models that predict the behavior of your customers. And when we talk about a single customer view, is if you want to do, I don't know, modeling of and predict things about your products, your orders, your inventory, your sales, your employees, your cases, your kind of, I don't know, your loan book, your policy book. For each of the entities that you want to make a kind of a prediction using machine learning, you need a single entity view that is exactly the same. One row per entity, one column for every bit of data you have scattered all over the organization, right? And gathered and manipulated in a consistent way, not just kind of as a kind of a manipulation. And the data volumes that you need for this depend a little bit, depending on the kind of the technology you want to use or the type of algorithm, but they can range anything between the low thousands for some of the most simplistic kind of machine learning models. But we talk in some cases about millions of data points that you might need in order to train some of the most sophisticated. So you really need to, like, this is not something that you can do kind of machine learning on the basis or on the back of just data that you capture kind of casually. This is data capture and data manipulation that you need to be running on an industrial scale, if you want.
So, data scientists, what do they need? What makes them happy?
What makes data scientists happy is I mean, kind of the key is in the job title. They are scientists, so what they're going to try to do is kind of follow a scientific process of formulation of a hypothesis, right? The design of an experiment to test a hypothesis, the gathering of data based on these single entity views that you give to them, or like in an almost like an unfettered way, plus the possibility of making their own kind of custom transformations if they have a bit of data that with a little bit of manipulation will actually yield better results. Give them the option not just of giving them like this massive catalog of data, but also the tools for some additional manipulation of that. And then what they will do is they will kind of run those experiments, test against the kind of the null hypothesis, which is the my kind of my initial hypothesis is wrong. This is a bit like the opposite of a criminal law. Your model is guilty or useless unless proven useful. So and which means that very often the result of this is going to be an hypothesis improvement. So hypothesis unproven, right? So my initial hypothesis was wrong, and I need to formulate another one and design another experiment and test it and do this all over again in an iterative process until we actually find something that is better, like and demonstrably better than almost like a coin toss up, right? And which is and it's very important that we actually make that make the proof that the model is better than a random choice in a scientific kind of testable, and there are loads of kind of statistical tests that you need to pass before you actually decide that your model is better than a random choice. Okay.
So, is there a trade-off between perfect models and perfect data?
There are always trade-offs kind of at the heart of ML, right? There's always, by the way, you'll never hear me say artificial intelligence or AI. So I'm only going to talk about ML. There's no I absolutely despise the expression AI. But there is essential. So the trade-offs at the heart of machine learning are the fact that you're trying to build a program that is going to try to make an understanding of the world, right? So that in the future can make predictions. Okay. And there we have the choice of how powerful or flexible we want our core algorithm to be. So in some cases, we have kind of a simpler, less powerful algorithms, right, that typically require less training data, that are typically not very sophisticated in the mathematics that they have underneath, right? Which means that when they will be prone to kind of not be great. They will be just kind of good enough, or kind of middling or good enough in terms of trying to like when you test the algorithm, it will give you predictions that are more or less okay. When you put into production, they will give you predictions that are more or less okay. And the good thing about those is that they're actually very easy to interpret or explain because the complexity of these models is relatively simple. So these are these are models that also where they have the advantage that training times and the volume of data tend to be small, lower. On the other hand, we have flexibles that are much more powerful and flexible, right? So we have algorithms that neural networks, for instance, come to mind, where they are really powerful. They can really capture a lot of the complexity of your real world phenomenon. But the flip side of that is that they require huge volumes of data, right? And not just volumes of data, but also computing resources and time for that. So you need to, because the flexibility of the model is huge. There are loads of kind of internal parameters and loads of things that the model needs to tweak internally. You just need to give them like massive volumes of data. You need to train on probably dedicated hardware over long periods of time, right? And your result can capture the complexity of the system kind of very accurately. But the inconvenience of this is that sometimes they behave, or they actually do behave like almost like inscrutable black boxes. It's impossible to give a simple reason of why your model predicts a positive or a negative result when you ask it to do a prediction, right? And also they're very prone to what's called overfitting, which is almost like in your student days when you revise to the test, right? They build a model that matches the kind of the complexities of the training data too well, but it doesn't generalize to data that it hasn't seen when you expose to kind of like when you put it into production. And there is and this also leads to an interesting problem with these very flexible, powerful models, that in many cases we require explainability. So say for instance that you want to know the criteria that led a machine learning model to accept or turn down a loan request. There are models that will tell you an idea why, which are the fields that it looked at in order to give you that decision. But there are very complex models where there are black boxes. You don't know why the model will actually tell you why it made that decision. And sometimes they can look at things that are nonsensical. And what comes to mind is an experiment that someone did with a neural network that classified to tell apart huskies and wolves. And it turned down that when they analyzed that model very closely, the reason why it was so good is because it was looking at whether the background had white snow or not, assuming that white snow meant wolves, whereas huskies that were more like the training, the data that they had, the images that they had trained the model with, they were wolves in the wild with snowy backdrops and huskies that were mostly kind of domestic animals. So the machine, the learning model did not look at the faces of the animals or the snouts or the ears or the tail or the coat or anything like that. They were just looking at whether there's a lot of white in the background. So sometimes the model is going to take kind of shortcuts, and it's going to be very difficult to tell whether the model is actually taking those shortcuts, which means that in cases, I don't know, things like, think for instance of medical diagnosis, you want to know that the criteria that the model is using to make a determination, positive or negative or whatever, is sound. And which means that sometimes you need to exclude really powerful models for certain applications on the basis that you need the predictions to be explainable, and you need the explanation to be kind of sensible.
So I'm gonna kind of go off the questions that I had for you. Something that you've just mentioned there, and it's something that's kind of piqued my interest. So machine learning in the real world. Does that not give us kind of ethical risks in letting machines handle decision making?
Absolutely, and to their credit, the kind of the giants of the machine learning world, they've at least recognized that, and people like Microsoft, for instance, are very vocal about the ethics of what they call the ethics of AI, which is, as I said, I despise the expression AI, but the ethics of machine learning are important. I'll give you a practical example. Imagine, for instance, that you were you were trying to decide whether to grant loans. You're a financial institution and you're deciding whether to grant loans, and one of your fields is ethnicity. Okay, and your past data has shown that certain ethnic minorities are actually have a higher chance to actually default on their loans. So what do you do? Do you factor in ethnicity on your as part of your criteria? Which, like, if it's strongly correlated with the idea of with a kind of a loan default, strictly speaking, you should actually factor that in. Or you can do the sensible thing, which is understand that ethnicity is a proxy for much complex kind of socioeconomic problems, which is the fact that, I don't know, ethnic minorities, they have a worse kind of economic outcomes in many cases due to discrimination. So it's how to say, people are not defaulting those loans because they are of a kind of a minority ethnic background. It's in many cases they're almost like defaulting on the loans because they are playing the game of life with harder settings as a result of the way that many people kind of interact with them. So it's a harder life. So as a result of that, lower salaries, worse housing, worse kind of health outcomes and everything. So chances are that they will kind of they will default. They might have a higher chance of default. So as a machine learning practitioner, it is essential that you don't build those coarse biases into your machine learning models, and you try to go back to the source in the sense that you actually look for not the I don't know, the racist or discriminatory proxy measure, that you actually try to understand the model much closer to try to get a better view that is a bit more kind of like a fairer and less prone to discrimination.
So what are some of the best practices that engineering teams can follow?
It's obviously, we talked about the kind of the data already. So it's you, like, how to say, you cannot do machine learning without a really kind of a mature data engineering practice, and you need to have kind of your kind of consistent, auditable, testable data pipelines. But that is kind of what you do in your data world is typically like a reflection what you do in your engineering world as well. So data cannot be the kind of the poor relation of your technical organization. So in machine learning you should, and in general data, in data driven engineering, you should be as strict as you are in your traditional software engineering. So you want to have a kind of a granular microservices design approach, or a what is called a lambda architecture that allows you to do kind of on the spot, complex on the spot transformations, so that your data scientists and your machine learning engineers can retrieve data and manipulate data on the spot. You want to have kind of a kind of service oriented architectures. You want to have a culture where peers review each other's experiments and code before actually contributing to your code base. You want to have things like functional and non-functional testing automation. You want to have automated pipelines to build, to build, periodically rebuild as well, and test and deploy your models. So an essential thing is something that we call a kind of a model drift. Is the fact that what your model learns with a static set of data is good for the time when the data was captured. But if the real world changes and you don't retrain that model periodically with a kind of a fresher data, you're effectively working with an understanding that might be lagging months or even years behind. So imagine that you build a model with the chatbot of how the English language was used, 5-10 years ago, right? It's going to struggle when you put it in front of people kind of with neologisms and with the kind of a new uses of the language. So it's very important to retrain your models periodically, and of course kind of try to use the same kind of architectural improvements that we do in our normal engineering. So adoption of things like containerization, adoption of cloud environments with infrastructure as code and everything. So try to apply that kind of those consistent engineering standards, not just to your requirements driven software engineering, but also to your data driven software engineering, and adopt something like ML ops. Just like you have a DevOps culture, you have an ML ops culture on your machine learning side.
Fabulous. And just to finish off, is there anything else that you would like to add about secrets of machine learning?
The secrets of machine learning is, well, the main secret. It's not a secret. It's in the literature everywhere. Is that 90% of models don't ever make it to production, right? So that there are loads and loads of kind of pitfalls there. Kind of starting with choosing the wrong problem. Not working with the right data, treating this as a one-off, as opposed to a process that you should try to industrialize with the aim of putting into production consistently. One of my favorites there, which is the fact that is having the machine learning and the data scientist teams kind of no work in collaboration with a close collaboration with your engineering teams. So have them report to your because the typical insights are used by marketing teams, is have them report to a VP of marketing, anything like that, and then be surprised that there are massive differences in the engineering practices that are followed on the data science side and on the regular engineering side. The people writing data driven kind of engineering modules, machine learning models, they really benefit from a close collaboration with the people building kind of requirements driven or top down engineering modules. So the best outcomes are typically in organizations that acknowledge that and don't segregate the developers and the data engineers on one end, and the poor data scientists to work on the different departments. So having all your kind of data people, the people generating the data and the people experimenting with that data, and the one saying kind of a common roof and following constant practices is typically the leads to the best outcomes.
Fabulous. Well, thank you for your time, Jorge. It's been great to learn more.
Thank you.